What's up, team? Let's get back at it. So now we're going to move on to the reaction coordinate or the energy diagram. You learned this in Gen Chem 1. I think the first time you saw it. Okay. All right, let's review it. What's the composition of an energy diagram or the reaction coordinate diagram? So we have you probably have seen a line like this, a curve like this, right? The line right here, the energy level right here show the energy level of the starting material or the reactant, right? SM stands for starting material. And we have an energy of the product right down here. What else we got? We have a transition state up top, the highest energy. The energy diagram tells you about the activation energy, right? So which is an energy that the reactant or the starting material have to overcome to be able to become the product. And we also have the net energy change from the product to the reactant. All right. Now, you may ask, why do we need to know this? Well, there are crucial information that we can take away from an energy diagram. All right. One of them, so thermodynamics information. It tells you how much product will form at equilibrium. All right. There are two types of energy diagram that you're going to see. On the left, start on the left side. Okay. On the left side, the energy of the product is lower than the reactant, right? In this case, so we know that energy is lower, it's more stable, and the reactant is less stable, which means that this at this equilibrium, the reaction will favor the formation of the product because it's more stable, right? KEQ going to be more than 1, and delta G or the net energy change going to be less than 1, which we call this type of reaction spontaneous, and we love a spontaneous reaction. Okay, gave you some examples. So we have hydrochloric acid in water. So this proton transfer happened right away. The pKa is -8. You guys know hydrochloric acid is a strong acid, right? So pKa -8. So 10 to the 8, that's 100 million times this equilibrium favor the product over the reactant. All right. So we love this. All right. Now the other types of energy diagram. So in this case, the energy of the product is higher than the reactant or less stable, right? Less stable than the reactant. And at this scenario, the equilibrium will favor the formation of the reactant, right? So the K equilibrium will be less than 1. And since the net energy change is higher, it's not spontaneous. All right, this type of reaction require energy input to drive or to force the reactant to become the product. Okay, so we don't really like this type of energy diagram, but you see both. All right, and we have this formula to show that delta G equal to negative RT log of K equilibrium. This is how you calculate the net energy change that gives free energy. Okay, so on the left side, when the energy level of the product is lower than the reactant or more stable, so we call it an exothermic reaction. On the right side, when energy of the product is higher, we call endothermic reaction. Now you have learned this before. Okay. All right. Let's try this real quick. Okay, how many steps are there in this energy diagram? You should be able to tell. So the first step is A is converted to B, second step B to C, and third step C to D. So there are 3 steps total. All right. How many transition steps are there? Well, there are 3 steps. So one step, one transition state, second step, second transition state, and third step, third transition state. So there are 3 transition states. All right. How many intermediates? Intermediates is species that form in the reaction and get consumed by the next reaction, so it will never show up in the net reaction, right? Or the overall reaction, what I mean. So there are 2 intermediates, so B and C, right? A becomes B, and B is produced in the reaction and get consumed and becomes C. And same thing with C, get produced first and then get consumed, become D. Okay. Now, which step is exothermic? So exothermic release energy, exo right here, C to D, only C to D, exo. So the energy of the product lower than the reactant. Which species is more stable, A or C, or totally A? Right, lower energy, so A is more stable. The overall reaction is endo or exothermic. Overall, so A to D, D is a little bit higher than A. Yep, higher, so this is endothermic reaction. All right, that's how we do it. Nothing's difficult in here. Okay. All right. Some reactions are exothermic, but they're not spontaneous because they have high activation energy, which is the energy that the reactant have to overcome so it can become product, right? So, like for example, some type of combustion, it's never just light up, become flame right away. Like just fire just come out of nowhere. You always need to add energy into it. You probably need to add a fire, a match, a high heat, so they can catch on fire. Okay. All right. Let's moving on.